Question 1. Redox reactions can be used to generate electrical energy from electrochemical cells. A student investigates the redox systems shown in Table 6.1 below. So you've got 6 redox systems there with their standard electropotential values given. Part A, define the term standard electropotential. Include all standard conditions in your answer. So, nice straightforward definition. Easy marks. Please make sure you learn your definitions and make sure you learn your standard conditions and state them all for this one. So, standard electric potential, the EMF or electromotive force of a half cell when connected to a standard hydrogen half cell under standard conditions which are 298 K or 298 Kelvin, 1 atmosphere pressure or 100 kilopascals, and 1 mole per decimeter cubed concentration. Part 2, or Part B. The student sets up a standard cell based on redox systems 3 and 4. Draw a label diagram to show how the student can have set up this cell to measure the standard cell potential. Your diagram should show the charge carriers in the circuit joining the 2 half cells and label the signs of the electrodes. Okay, so biggest mistake students make with this is they misread the question and pick the wrong equations. Now you're told it's systems 3 and 4, so those 2. All right, ignore everything else in that table. You're only interested in systems 3 and 4. Okay, so it's the vanadium 3, vanadium 2 system and the copper 2 and copper metal half cell. So combine the 2 together. Let's start with the basic drawing first and then we'll focus on the labels. Okay, so 2 beakers. Make sure any diagrams you do are nice and clear. Solutions. We're going to have 2 electrodes connected to each other via a voltmeter. And then you use a salt bridge connecting 2 systems up as well. So label the salt bridge. Always advisable to do that. You shouldn't need to label the voltmeter. It's obvious with the symbol what that actually is. All right. So system 3, if we say this side is the vanadium half cell, so in your solution in there, you're going to have vanadium 3 plus ions and vanadium 2 plus ions, both at 1 mole per decimeter cubed. And on the other side, you're going to have, for the other system, copper 2 plus ions at 1 mole per decimeter cubed. Okay. The electrode for the copper half cell will be copper metal. The electrode for the vanadium half cell will be platinum. Okay, this is an ion half cell. You've got V3 and V2, so the pair of them together means you need a platinum electrode, otherwise the cell won't work. You can't have a vanadium metal there because then you'll get a redox system setting it between the vanadium metal and the vanadium ions, and it's going to cause problems. So you have to, any ion-ion system, the electrode is an inert metal, and platinum is the obvious one to go for. Okay, so show the charge carriers in the circuit joining 2 half cells. Okay, so the charge carriers are going to be the electrons, and they're going to be transferring from the negative to the positive. Okay, now looking back at your electrode potentials, you can see that the vanadium half cell has got an electrode potential of minus 0.26, so and the copper is plus 0.34. So your vanadium half cell will be your negative electrode. So this side is negative, and this side is positive. Okay, therefore electrons are traveling in this direction. And then in the salt bridge, you would have your ions traveling to complete the circuit. So remember, the salt bridge is soaked in, so we just move the diagram up so you can actually see it. The salt bridge is soaked in an electrolyte which won't react with your 2 chemicals. It's normally potassium hydroxide or something like that, but something that's not going to react with the 2 solutions in your cell. Okay, and there we go. So 5 marks for this. And the mark scheme, the marks come from 1 mark for the copper electrode, 1 mark for the platinum electrode, 1 mark for the salt bridge labelled, and a complete circuit with voltmeter. So making sure that your electrodes and your salt bridge are submerged below the level of the solutions in your beakers. 1 mark then for the copper half cell being the positive electrode, and the vanadium half cell being the negative. So it was not 1 mark each, but 1 mark for both of those being shown. And 1 mark is for stating the electrons are in the wire, or showing the electrons are in the wire, and the ions are in the salt bridge. I've missed that one off there. So I'm just going to label that as ions in the salt bridge. They are the charge carriers. So a lot of information on that diagram. I've drawn it a bit small there. I hope you can see that clearly. But be careful when any diagrams like this, any questions like this, make sure you look at those bullet points and understand exactly what they're referring to there.